Hello, my name is Tom Wallace. I'm taking my master's degree for computer science at Brock University. Today I'll be presenting my submission to the data challenge track, identification and classification of JMH microbenchmark states using time series analysis. I'll be going over the problem at hand, some techniques, related work, our methodology, conclusions, and possibilities for future work. The data provided for the data challenge track is Java microbenchmarking harness benchmark data from various programs. This data is in the form of a time series, meaning it shows the change in value over time. In this case, it measures the time taken for an execution across each iteration. The idea I was given was to apply pattern mining techniques, which attempt to draw conclusions from repeated patterns in data. In researching time series analysis, we discovered some methods provided by Python packages which appeared useful. In a similar vein to the original paper the data comes from, we attempted to use these for determining the state of a given benchmark, steady or non-steady. We also briefly analyzed its ability to detect performance anomalies. The primary method we want to analyze is the matrix profile method. In essence, it creates a secondary graph which displays which parts of the original time series are the most similar to each other by comparing subsequences of a given window length m. So these highlighted parts are the windows. Each point on the matrix profile graph indicates the difference between the subsequence starting at the corresponding point on the main graph and its most similar subsequence. Lower points on the graph have higher similarities, with the two lowest representing the closest match, referred to as a motif. These 2 points highlighted on the top graph are the most similar to each other. The highest point on the matrix profile graph is the most unique, with it and other peaks referred to as discords. So points like here, here, so on. An additional method is called change point analysis, which attempts to break a time series into distinct phases separated by change points. So on this example graph, each change in background color is a change in change points. Each section is distinguished by a significant change in the mean from one to the next. So we can see that all of these different segments are noticeably different. There are various other papers and resources which aided our research regarding the data and these techniques. Of course, there's the paper that the data challenge is based on, where the data comes from. Both the previously mentioned methods, in addition, are implemented in Python libraries. Stumpy implements the matrix profile method, while Ruptures implements the change point analysis method. In addition, a paper by Barrett et al. Describes and implements a method for determining the state of a benchmark using change point analysis. There are 3 research questions that we want to consider. How effective are motif discovery in the matrix profile in aiding identification of steady state and non-steady state benchmarks? How might motif discovery in the matrix profile be used to detect performance anomalies? And how comparable are the results obtained by motif discovery to those obtained by change point detection? For our first question, we applied both methods to a sample of the benchmark data. The goal was to determine if there is a statistically significant difference in values between the matrix profile graphs of steady and non-steady state executions. Change point analysis in this case is only used to differentiate between the two states. The results we found by comparing the average, min, max, and mean of the matrix profile graphs and applying a 2-sample t-test seem to show a notable difference between the two types of benchmarks. This suggests that the matrix profile method could be useful in state analysis. The second question is a bit less clear-cut. Though we want to observe if the matrix profile could be used to detect performance anomalies, the data does not give enough the information to definitively say whether an anomaly occurs. So the analysis in this case is mostly conceptual and qualitative. As a result, I simply considered patterns which tend to correlate with anomalies, so spikes, for example. For this purpose, discords tend to be more useful, so for example, we see a large spike here notified by the discord, the red line. However, this method can miss other anomalous behaviors, particularly if it happens early enough to dominate a majority of the time series. So we see here there's a massive increase in state and 2 overall changes in state, but it's not accompanied by a major difference in the matrix profile. For our third question, we decided to directly compare the two methods. Because change point analysis is a proven, useful method for state classification, we want to observe whether the matrix profile can find similar results. A correlation would be better if the change points are frequently located very close to or within the motif and/or discord windows. So on this example graph, we see 2 points where the change point is within the motif window. The results found with this method are shown here. We can see that the correlations between the two methods are generally stronger when steady state is not achieved. Although the correlations are not significantly stronger, we believe it's still a difference worth looking into. The experiments performed are not entirely formal nor exhaustive. Regardless, we believe they demonstrate the potential of the matrix profile method for benchmark state analysis and anomaly detection, at least enough to warrant further research. If we were to propose some ideas for continuing this research, we would start with the methodology. It would be important to perform more thorough experiments with stricter methods to achieve more definitive results. Regarding research question 1, it could also be possible to compare the matrix profile graphs between different forks of the same program. For example, to see if steady-state forks are notably different from non-steady-state forks. For research question 2, which was admittedly lacking, it would be necessary to create a more thorough methodology allowing for a quantitative analysis of the premise.